Hello there, welcome back. We are on part 5 of machine learning basics. So we started with linear regression, logistic regression, got into optimization, and then talked about variance versus bias trade-off, which is really these competing forces of the model to capture all of the training data, but we still want it to generalize to new data very well. And so we're going to be talking about regularization in this part, and that's really essential to try and capture this balance of these two forces. So let's go ahead and get started. Okay, Control L. Yes, we are on part 5, so yeah, very good. Okay, so let's start off with a true-false question. Logistic regression is an example of regularization of a linear model. Yeah, I mean, I really, threw this out just to see if people understood the concept of regularization. The truth is, this is false. You can regularize both a linear model or add regularization to logistic regression, a nonlinear model. So it's not an example of that. Again, logistic regression was an example of, really a linear model combined with a sigmoid nonlinear function. Okay, so we're going to get into what L1 and L2 regularization is, but let's go back to the example from the variance versus bias trade-off. So we had this true function, now shown in orange here, and then I chose a number of different data points along this and added noise to them. So that's what you see with these blue dots. These are all the noise that I added. But this is the underlying function. And so we want a model that can capture the underlying function, not a model that can capture the noise. So again, this 20th degree polynomial linear regression model that's shown in blue trying to capture all the noise, that is what we don't want. That is an example of an overfit model. And then what I've shown below is actually one that's more appropriate. So we change this lambda parameter, which I'll talk about in just a second. And this is an example of regularization. So after regularizing this same model, so this is the same 20th degree linear regression model, we've regularized it, and now it actually does a fairly good job of capturing what the true function is. So what does this lambda parameter and regularization actually mean? What it means is if we go back, if you remember J is our cost function. So this first term right here for a regression model, this is your mean squared error. This is the average of our L2 loss functions, but we've added this second term. So in this second term, we have a parameter lambda, and we're going to multiply it. Look, we're going to square all of these theta values, theta 1 through however many thetas we have. In this case, with 20th degree, we have theta 1 through theta 20. So there's 20 terms. We're going to square them, and we're going to sum all of them. And this acts as kind of a penalty on those theta parameters getting too large. And it turns out that for a lot of overfit models, the way that it overfits and tries to, capture all this noise like this upper plot is to actually make these theta parameters very large. So this is going to act to try to reduce the cost function by reducing the size of these theta parameters. And this lambda term is an example of a hyperparameter. So this is something that doesn't show up in our end model, but it is important to training, because it affects this cost function. This example of L2 regularization just means that we're squaring this theta parameter. And this is often called ridge regression when it's combined with linear regression. It's not the only penalty term that you can add. Another common one is called, an L1 regularization, and it's called lasso. And you can see what the acronym stands for: least absolute shrinkage and selection operator. And the big difference is that instead of taking theta 1 through theta 20 and squaring them and summing them, you're going to take the absolute value of each of them. And then summing it and then multiplying by a lambda parameter. And there's also elastic net. If you can't decide on L1 or L2, maybe you include both terms. Probably not as common, but could also be, something to consider. And what I talk about down below, lasso tends to pick winners, so to speak. It will zero out a lot of these theta parameters if you choose a large lambda. So it tends to pick the terms that are good for the model, and zero out some other terms. Whereas ridge regression, it tries to shrink the coefficients of all of the terms, in order to reduce that penalty function. Oh yeah, so what happens as we increase lambda, right? I mean, we went from 0 to 0.01, and seemed to do a good job. So can you just continually increase? Do you want a really large lambda value? And the answer is no. So what actually happens if you choose a really, really large value? I mean, obviously infinity is the largest of those values, is you added so much of a penalty to all these thetas that it's going to want to reduce these theta values to 0. Now notice that this is 1 to the number of your theta values. It's everything from theta 1 up to, theta 20 in this case, but it's not theta naught. And so what's left behind and isn't penalized is this constant. And so, if you penalize this too much by selecting too high of a lambda value, then what ends up happening is it will return a model that's a straight line, where it's only really fit the theta naught parameter. And again, this is a good example of how we started with an overfit model, 20th degree linear regression model. And through this lambda parameter, we not only tuned it back to get a good model, but we tuned it all the way over so that it actually created an underfit model. Oh, there's Han Solo again. Yeah, tired of waiting. Take orders from one person, me. He probably wants us to get into neural networks, and we're almost there. Just trust me on this. It's going to happen very quickly, where we go from linear and logistic regression and regularization, and we'll talk about neural networks next. So yeah, now we're going to talk a little bit about training set, dev set, or validation set, test set. What does this all mean? So here, assume that you don't know what this function looks like. So actually the nice thing, even though we created this synthetic set, nowhere in fitting these models did we know what the true function looks like. And so it does become difficult. I mean, if you think about it, this top model has a lower error than the bottom model, because as it's trying to overfit and capture all of this noise, it's reducing the loss functions for each of these points, much more so than this model down here. So even though visually we can see, okay, the model on the bottom is capturing kind of the underlying trend a whole lot better than the model on top, the error doesn't show that. So the way we have to address this is called cross-validation. And what it effectively means is that you're going to take all of your data set and you're going to divide it up so that you can validate that you aren't just creating a model like that above that's going to not do a good job at predicting on new data. And yes, this kind of elicits this this cartoon. Again, great website, xkcd.com. All sorts of kind of witty takes on different science topics. This is your machine learning system. Yep, you pour data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. So yeah, I mean, you can cheat yourself with this, but the idea with cross-validation is that you're going to withhold some data so that when you train your model on the training data, you already have holdout set that you can evaluate how good your model is on data that it hasn't seen during training. And so in doing that, that allows you to, make a fairer assessment of how good your model is. So one of the ways that they do this is through k-fold validation. While you can just separate it into training and test and do that once, in practice, a lot of people like to separate it out. So how k-fold validation works is, imagine you have, 1 to n, a whole bunch of different examples in your data set. And you want to train a linear regression model, for instance. You're going to actually divide this up into 5 different bins. So you have 5 different bins. And during one pass, you're going to train that model on bins 2 through 5, and then you're going to evaluate it on bin 1, the data in bin 1. So that's going to give you kind of an error for that validation set. Then you're going to train that same model using 1, 3, 4, and 5, and you're going to test it on bin 2. And then you're going to train it on 1, 2, 4, and 5, and test it on 3. And so you continue to do that, and you can add up or average these errors, for each of these 5. I'll say they're different models. They're the same models, but they're going to have different model parameters because of the data that they're trained on. And that error from all of these kind of orangish bins is actually a good test case of like how well the model does on data that it wasn't trained on. So with that, you're kind of validating the model of how well it does on data that you didn't train it with. And k-fold validation, I just showed 5, but you could certainly divide your data set into any number of different bins or folds. So k equals 10, you're going to divide it into 10 folds. Again, this first one, train it on 2 through 10, and then test it on, the first fold, and so on and so forth. The most extreme one is called leave one out cross-validation. So let's say n is 100. You've got 100 different kind of observations in your in your data set. So for the first model that you're optimizing or training, you're going to use 2 through 100 and you're going to test on 1. The second one, you're going to use 1 and 3 through 100 and test on 2. So each time you're using all of the data except for a single kind of observation or row within your data set, and then you're testing on that. So in the end, you're going to end up training 100 models, in order to compute this kind of validation error. So that would be the most extreme, and it works fairly well for these linear and logistic regression models, for very simple models, because these can train very quickly, when you throw them into a programming language like Python. Now, I haven't talked yet. You have this training set. This is what you're going to train your model on. You have this validation set. This is, again, a test of these models. And then you have a test set. So you always want to have one portion of a holdout where, after you've done everything else, validated your model, trained it, let's go ahead and see how well it generalizes to new data. And so why you have 3 of these? Okay, so training set is to train and optimize your model. A lot of times what this validation set is used for is you can select different hyperparameters. So you might want to select different hyperparameters. Remember, we just talked about lambda. So you might want to test at different lambda levels, what is the validation error corresponding to those? And that will give you some insight for, okay, what is the best lambda value? So then you can choose that hyperparameter at the optimal hyperparameter. You can retrain your model using that. And then you still have this holdout data. So you still want to kind of test it on that and make sure that it's doing well. So what does doing well mean? Well, you would like it to do just as well in terms of error on this holdout data, this final test data in green, as it did on your validation set, for instance. And that's kind of what I'm showing here. Again, you have your training error where you're going to train this model. You have this validation set or dev set where you're going to train hyperparameters. I say hyperparameters here. You can also compare different models. And so a lot of people, it's so easy with some of these simple models to select a number of different models, use the same training data, calculate the error using this validation set, and then you can compare that between the different models in order to select the one that performs the best. And then with that model, you would your final test is this test holdout set. So, that's why typically you would divide into these 3 sets just to make sure that you have a good machine learning model, that you're choosing the right hyperparameters, and model complexity and regularization in order to obtain sort of this optimal machine learning model that's not overfit or not underfit. So let's just go to an analogy, right? So here's kind of the analogy of what we've learned. This data is this crude oil that we need to refine a lot of times. I didn't talk a lot about cleaning the data, but this clean data is really what provides the fuel to these big machine learning models. I have talked a little bit about like AI, artificial intelligence, is this, kind of shiny sports car. It's a big complex system. There's a lot of architecture built around it. But machine learning is often, what powers it. These days, machine learning is really what makes, AI, perform so well. These machine learning models are going to have lots of model parameters, which are going to be optimized for the performance of that model. And hyperparameters, you can think of having all these model parameters to tune your vehicle, and hyperparameters being something like, okay, how quickly you turn it, so it's almost another level on like how they act in order to allow you to better train the parameters for performance. And then, this separation of these different data sets, when you're talking about this training and validation and test data set, let's just imagine this sports car in different operational environments, or OE. The first case, maybe you train your sports car in city driving. You can test it in city driving, and that can be good. But then you might try to test it in a forest domain or, in a desert domain. And so there is a balance here between, if you test it in one domain, does that mean it's good for all domains? And in reality, it doesn't. It means that if you train it in one domain, it probably is optimized for that one domain, which can be good in certain contexts, but may not mean that if you take that sports car, which is highly tuned for, a city driving domain, that it's going to do well in sort of a desert or forest environment. Now, you could take and train it in a few different operational environments, and that might be good, but that may not mean that it accurately performs, in something that it wasn't trained on. You can train it on all of these different environments and train hyperparameters for this car, but does optimizing it for all environments mean that it's suboptimal for any one of these? And I think it actually does. And so, this is just kind of the analogy that you have to think through. When you're thinking through, we have all of this data, and how do we separate it out? How are we training our model in order to really have it perform well in the environment that we want to put it in? So with that, I'm referring back to this whole list of definitions. We've certainly covered a lot at this point in terms of kind of the basics of machine learning. And now we're going to start moving into neural networks and how that works. And really, you needed to have kind of this baseline understanding of these key concepts. Again, linear and logistic regression and optimization, variance versus bias trade-off, regularization. All of these are going to enter into our description of how these neural networks work. So with that, yes, thank you, and we'll go ahead and close this section out. So thank you once again. May the course be with you, and we'll see you in the next set of videos.